Hi everyone. To take this a little farther into the world of artificial intelligence and AI and data modeling, we have come chronologically from the 1890s through the 1950s, through the 1980s, and through the 2000s. Now, data visualization and data science and meteorology really are banded together. It's a great career for people who are interested in data. And let's explore a little bit about what these data scientists do with all of this mountain of data that comes in every hour. There is analysis, of course, from the surface and the upper air charts that figures into numeric modeling, and we'll talk about that. That numeric modeling goes into modeling the atmosphere from the ground all the way up to the ionosphere and the stratosphere. And there are predictions that are based on numerical models as well, and that involve mathematical equations in every sector of the atmosphere. So just to give you an idea of what we're talking about for models, this on the bottom has 5 models that are frequently used and compared. So all of this data comes down as raw data and observations that we've talked about. Then it goes through an ETL process, which is extract, transform, and load, basically getting the data into a format that you can look at, cleaning up the data, and loading it into the models. And some of the models that we're talking about here. This is the European Center for Medium Range Weather Forecasts. You'll see it has something very similar to the what's a German model that's frequently used, ICON, and that is a German name that is translating. And you'll see that it's very similar to the first, but it's missing a bit of data in here that is in the first model. A lot of these models deal with uncertainty in the data in different ways. And that's what you're seeing here. You're also seeing differences in how this model looks at this disturbance around Florida based on the data and the statistical degree of uncertainty. A very, very common model is the GFS, which is the Global Forecast Systems model. And there are all different types of this model, but the way the data is handled is the overarching pattern that you're looking for here. So this looks at basically the same things, but as you note, it doesn't have some of the infrared that the other models note in this area up in the maritime Atlantic area. And then the NAM model, North American Mesoscale, very popular model. So you'll see that, and you'll also see HRRR, High Resolution Rapid Refresh. I think that most commonly you're going to see the GFS and the NAM models if you look into it. Really fascinating to look at. And they take all the data that was presented there. This is basically raw data that they're looking at here, and then they really fine tune it to get to a forecast. They want to get to a forecast via a prognostic chart. It's called a prog, right? So you go from model charts to prognostic charts to forecasts based on looking at different prognostic charts from different models. And you can see that these are quite different in the way the software interprets the data. These are all ground level charts that we're looking at. And so they all use the same MSLP, which is a type of ground mesoscale data, but they present it in very different ways. And so you'll see that the European and the global, the GFS, approach it in quite the same way. You will see differences around the Gulf of Mexico in some of these tracks in here, just little differences. And of course, when you look at the ICON and the NAM and the HER models, you're going to see some pretty big differences in the way the data is interpreted. A good meteorologist will take all of these models, take a little bit here, take a little bit there, and focus in on his or her experience to find out what they are looking for in terms of predicting. I know that last winter, right before Thanksgiving, we were dealing with the fact that, oh, they're not going to be able to fly the balloons in the Macy's Thanksgiving Day Parade. Last year, it seemed like life was a lot easier, right? There was one model out of the GFS system that really nailed some of the data and really nailed in the prediction very well. And it was pretty easy to find that on some websites that I go to. One of the really good websites is tropicaltidbits.com. tropicaltidbits.com. Very cool stuff. So now you'll understand a little bit more about what they have there. When it comes to these models, the charts that you see there are not generally the final charts. These models will be run time after time after time in what's called ensemble forecasting. And what they do is they take the same model, the GFS model, for instance, and they run it with different data based on the error content of the data that they suspect. So if it has plus or minus 0.5 degrees centigrade, all right, they'll run it at the minus 0.5, at the 0, and at the plus 0.5. And they'll run the model 3 different times. They'll run the model 5 different times, 10 different times, 15 different times, looking for variations. That creates what's called a spaghetti plot of one type of model. This might be all GFS for snow forecasts, for snow totals in Boston. And it all comes out of one model done over and over and over again with different sources of error put in there statistically. All right? It allows for that error. And then it comes up and you decide which one you're going to go with. Generally, I'm just going to go back here for a second. Generally, you go with the median or the mean right in here. All right. And you say you could have anywhere from 3 inches to 51 inches, but we're probably going to get 24. And you hear that all the time. Now, I want to show you how you can combine ensemble forecasting. This is a visualization of the top of the world, of the North Pole, and it's looking for long wave and short wave long-range forecasting. And what you're doing here is you're taking a spaghetti model of red, and there must be 18, 20 lines in there of different variations of the same model for long waves in here. All right. And you can combine that. That is at a higher altitude. All right. You can combine that with shortwave activity at a lower altitude. And this is a spaghetti ensemble, or a spaghetti plot, an ensemble forecast for short waves. And you could combine the two of them and look at the long waves versus the short waves in here. This is combined ensemble forecasting, used quite often for Farmer's Almanac. Why do all these models go so haywire? Well, they do have an avalanche of data, but there are many areas that are not covered well. For instance, you have 2 global satellites going over the North Pole and South Pole and everything in between, but that's only 2 points of data, and you're missing a lot. There's not buoys in that area. There's not a lot of flights that go over that area. There are some. So there are sparse observations in some regions. It's a big source of error in the computer forecasts. And then, of course, there's always errors in the models themselves. So that's why it's an art. Forecasting is an art based on a lot of formulas. There are time frames for forecasting, nowcasting, all the way to seasonal and everything in between. And this is an important point. It is accuracy versus skill. Now, you can be pretty accurate with your forecast. You even noted that in your first lab. You could pretty much do pretty well at 2 hours. And the National Weather Service does very well in anywhere from 12 to 24 hours. Quite accurate. And skill says that you are better at longer range forecasts. And skill says that you are better at pattern recognition and pattern knowledge. So when you're looking into developing skills for forecasting, you have to employ all the data and all the models and then your own experience to know the patterns. So we're going to go through 3 patterns that are pretty generalized for the Northern Hemisphere, and you can apply that to some of the forecasting that you'll be doing soon. First of all, if you want to know where a pressure system is going to move on the map, then you need to check the 500 millibar winds. And your surface pressure system will move in the same direction as the 500 millibar winds at about half the speed. That's a pretty standard number 1 trend that you need to know. Second, you need to know that your lows are going to move with the wind, yes, and they're going to trend to the region of greatest pressure drop. In other words, where these isobars are tightest. And you've been hearing about that. So this low is going to move into this area because this is where the isobars are tightest. And the other thing is that a mid-latitude cyclone, there's not one on this map, but you'll usually see them up by the Great Lakes. A mid-latitude cyclone will go in the same direction that it's been going in the last 6 hours. Give or take a little bit of the local patterns, which you get to know. So the mid-latitude cyclones will be the same direction, the same speed as in the last 6 hours. Give or take, you might have it move around some mountains or hillsides or foothills, but you'll know those local patterns. So I hope that helps you out. Just to go over briefly, there's many different forecasting techniques. This persistence or trend forecast or analog forecast are really based on experience. Statistical forecasts are associated with meteograms and aviation, and the climate, I should take that back and change that a bit. Then you can get into the numeric forecasts and the artificial intelligence forecasts. So I'm going to change this slide up a little bit. I hope you enjoyed chapter 9. I hope you do some good forecasting.